All right, let's get into it. You know, we see patterns all around us, every single day. But how do we actually describe them? How do we nail them down? Well, today, we're going to break down a really simple but powerful idea on math that governs everything from nature to finance. We're talking about sequences.
So, to get our brains warmed up, let's start with a little puzzle. Just look at this list of numbers on the screen. 3, 5, 7, 9. What do you think comes next? I'll give you a second. If you're thinking, hey, it looks like you're just adding 2 each time, then you are absolutely on the right track.
And if you said 11, you nailed it. What you just did there, that's recognizing a mathematical sequence. It's really just a fancy way of saying it's an ordered list of numbers. We call each number a term that follows a very specific rule or pattern.
Now, when you talk about sequences, they basically come in 2 main flavors. First, you've got your finite sequences. These guys have a clear stopping point, like the first 5 even numbers. And then you've got infinite sequences, which, yeah, you guessed it, just keep on going, forever. Pretty straightforward, right?
So, knowing what a sequence is, that's one thing. But the really cool part, the interesting question, is how do we actually create them? How do we write the blueprint for one of these patterns?
To really wrap our heads around how these things are built, let's use an analogy. I want you to think of a sequence kind of like a marching band trying to get into formation. See, every single person in that band needs to know exactly where they're supposed to stand to make that perfect shape. And it turns out there are 2 main ways to give them their instructions.
And this slide just breaks down those 2 instruction sets perfectly. On one side, you have what's called the general term. Just think of that as giving every band member a super precise GPS coordinate for their spot. On the other side, you've got the recursive rule, which is a lot more like telling each person, hey, just look at the person in front of you and line up based on them. See? 2 totally different methods to get to that same perfect formation.
So let's dig into that first method, the general term. This is basically one single all-powerful formula. If you want to know the value of, say, the 50th term in the line, you just plug the number 50 into the formula. That's it. You don't need to know what the 49th term was or the 48th. It's a direct map to any single point in the entire sequence.
And this shows you just how powerful that is. Remember our first little puzzle? Well, the general term, the GPS coordinate for that sequence, is 2n plus 1. So what if you wanted to know the 100th term? You don't have to sit there adding 2 over and over again. Nope, you just plug 100 in for n. So 2 times 100 is 200, plus 1 is 201. Boom, done. So efficient.
Okay, now let's check out that second method, the recursive rule. This is the follow the person in front of you method we talked about. With this one, each term's value completely depends on the term that came right before it. But here's the catch. You can't start a chain reaction without a spark, right? So recursive rule always needs a defined starting point. Let's see how this actually works. Okay, so we're going to start with the number 3. The rule says to get the next term, you take the last term, multiply it by 2, and then add 1. So for term 2, we take our starting number, 3, multiply by 2, that's 6, add 1, and we get 7. Now for term 3, we take that 7, multiply by 2, that's 14, add 1, and we get 15. See how each step is built entirely on the one that came before?
Okay, so now that we've got our 2 blueprints, the general term and the recursive rule, let's take a look at some of math's greatest hits, some of the real superstars of the sequence world.
So you have your basic types. Arithmetic sequences, that's where you just add the same number over and over, kind of like our warm-up puzzle. Geometric is where you multiply each time. But hang on a second. Look at those last 2, Fibonacci and Mullitou. They look like they have the exact same rule. So what gives?
First, let's meet the celebrity of the group, the Fibonacci sequence. This one is famous. It shows up in nature all the time. And the rule is so simple. You just add the 2 previous terms to get the next one. So 1 plus 1 gives you 2. Then 1 plus 2 gives you 3. 2 plus 3 gives you 5, and on it goes.
And this brings us to something really fascinating. Now look at the Mullitou sequence. It uses the exact same recursive rule as Fibonacci. Add the last 2 terms together. So why on earth is it a completely different sequence of numbers? Well, it's all about the starting point. Fibonacci starts with 1 and 1. Mullitou starts with 4 and 1. That one tiny change to the initial conditions generates a totally unique pattern.
And get this isn't some ancient concept dug up from a textbook.
The Mulatu sequence was only introduced back in 2011 by Professor Mulatu Lema, a mathematician from Ethiopia. It's just a fantastic reminder that people are discovering new patterns and new ideas in math all the time.
So, after all of this, after looking at how these patterns are built and checking out some famous examples, what's the big idea here? What should we really walk away with? It's this. This is the crucial point. Whether it's a simple instruction like add 2 or a rule like add the 2 before you, the real magic of sequences is that you can generate these incredibly complex, beautiful, and sometimes unpredictable patterns from very, very simple starting rules.
And that really leaves us with one final thought. We've kind of peeked behind the curtain and learned the grammar of patterns, the basic rules that write these hidden numeric stories all over the world. So now that you know how to look for the rules, what hidden patterns, what sequences are you going to start seeing in the world around you?